Good morning, myself Dr. B. Ravi Chandra, and today I am here to discuss about a fast Fourier transform algorithms. In the previous sessions we have discussed about the discrete Fourier transform, and we have seen some different types of topics related to the signals, systems, and different types of signals, different types of systems, followed by the properties of discrete Fourier transform and related problems. We have seen all that in the previous two sessions. Today we will discuss about the fast Fourier transformation algorithm. So why we are going with the fast Fourier transform when compare it to the DFT? Although we have the DFT, why we are going with this particular algorithm, which is fast Fourier transform? So we will discuss what is the introduction, that is the contents which I am going to discuss in this particular session is why we are going to use this fast Fourier transform when we consider the DFT. What is the improvements over DFT over FFT? Okay. Next, computational efficiency of FFT over DFT, fast Fourier transform, and small two properties considering this, which is related to the properties which were used in this particular fast Fourier transform, followed by methods of FFT. So in this we have some different types of method. In this session we will cover one particular method and very important, which is decimation-in-time FFT algorithm, and what are the computational complexity in the FFT algorithm, followed by the twiddle factor, the main important topic, which is nothing but the twiddle factor, and we'll see what is the step-by-step signal flow graph, which is nothing but the decimation in time, one method which we are going to discuss. We will see the step-by-step how this signal flow graph is going to design, and finally we will take one problem and we'll solve this particular algorithm, which is DIT FFT. So here, coming to the introduction of fast Fourier transform. So why we are going with this fast Fourier transform instead of this DFT, discrete Fourier transform? What is the difference? What is the main consideration and main advantages in the FFT over the DFT? So what it says, you can see here, if we use the DFT in the digital computers, by solving the problems in the digital computers, what are happening means we had already seen in the problems which we have solved in the previous sessions, where we have seen some number of additions and multiplications happened in the particular problems. So that is the major drawback which is present in the DFT. So what it is saying, the time taken to evaluate a DFT, so in the digital computers, why? Because mainly involvement of the multiplications, number of multiplications and additions. So this is one of the major drawback which is present in the DFT. So the time taking to evaluate the DFT. So how this time is going to take means, because of number of multiplications involved and number of additions involved. So by doing some number of multiplications and additions, what happening? The digital computers become slower. That is, the operation becomes slower. This is one of the disadvantages in the DFT. So what is the number of multiplications involved in the DFT means, you can see here with the DFT this number is directly related to n square, that is number of multiplications. How many number of multiplications that happens in the DFT is that it depends upon the value of n. So if n is equal to somewhat 256, that means how many multiplications it involves? It involves 256 square, that you can see here. So if the n value is 256, then means how many number of multiplications it should solve means it should solve 65536 multiplications. So with this number of multiplications, what happening? The operations become slower. So that's what he's saying. N is chosen to be at least 256. If I choose n is as 256, how many multiplications, how many computationals will happens means here it happens 256 square. So and computational speeds become major consideration. The speed becomes decreases. So highly efficient computer algorithm. So to overcome this particular problem, what the two known scientists, who is Pullaiah and Tukey, they have introduced a new algorithm which is nothing but fast Fourier transformation. So the two scientists named Pullaiah and Tukey. So they introduced a fast Fourier transformation, and we call that particular algorithm as Pullaiah-Tukey fast Fourier transformation. They rely on the fact that standard DFT involves a lot of redundant calculations. That means the steps which are repetitively involved in the DFT will be overcome by this particular fast Fourier transform. Final conclusion with this particular slide, I can say that why we are going with this particular FFT instead of DFT means to improve the operation of the particular systems, the particular digital computers. Fine. Now, here you can see the computational efficiency of FFT over DFT. How these FFT overcomes the drawbacks that is present in the DFT. Now see here, this computational DFT has been divided into two types. One is divide and conquer approach and another one is linear filtering with DFT. This already we have seen in the previous problems, but presently we are going to concentrate on this particular technique, which is divide and conquer method. So that means the computation of DFT has been divided into two types. One is divide and conquer methods and another one is linear filtering with DFT. So these divide and conquer, it has been subdivided into three parts. One is Radix-2 FFT, Radix-4 FFT and split Radix FFT. So these are some different types of fast Fourier transform, depends upon the Radix. So the Radix means Radix value 2, 4 and it also we have another method which is nothing but the split Radix FFT algorithm. So here these Radix algorithms, FFT algorithms are subdivided into two types. One is DIT FFT and DIF DFT. That means, sorry, here FFT, DIT FFT and DIF FFT. So DIT is nothing but decimation-in-time fast Fourier transform and decimation-in-time, decimation-in-frequency fast Fourier transform. In this session, we will discuss about what is DIT FFT and what are the advantages present in, followed by some steps, what is the procedure happens in this particular DIT, followed by a problems. So this is the division, that is classification of the computation. That means what happens in this particular divide and conquer, the given sequence will be subdivided into n by 2, n by 4, then the execution will happen in that particular subdivisions. So we will see that in the upcoming slides. Fine. So this is the computation of the DFT classifications. Now we will recall the things. We will recall the equation which is DIT, DFT and IDFT. We know that DFT is the equation, that is xp is equal to summation n is equal to 0 to n minus 1 xn e power minus j 2 pi by n np, which is DFT equation, followed by the reconstruction part which is IDFT, inverse discrete Fourier transform. So inverse discrete Fourier transform, which is nothing but xn is equal to 1 by n, the scaling factor 1 by n, summation p is equal to 0 to n minus 1 capital xp e power j 2 pi by n into np. So just recalling the equations of both DFT and IDFT. So with this, how many, what is the computation that happens in the DFT? That means if we solve some particular sequences given with the help of the DFT, how many number of complex additions and how many number of complex multiplications means, you can see the formula here. So if I'm going to do some problems related to DFT, if I'm computing some problem related to the DFT, in that particular problem, how many number of complex additions we are going to solve and how many number of complex multiplications we are solving means, see here, n into n minus 1. So n into n minus 1 complex additions we are solving, and similarly how many multiplications we are solving. Just in the previous slide we have seen, that is the complex multiplications that solved in this particular computation of DFT will be n square. Okay, so we can see that in a particular computation of the DFT, how many complex additions, it is n into n minus 1. And how many complex multiplications, it is n squared. So these number of additions and multiplications are going to solve. So now on our agenda is to overcome this particular number of complex additions and multiplications. That's why we are going with the FFT. So we will see what is the direct computation of the Radix-2 FFT. Now here see, by solving the particular same problem which is we have solved in the DFT, there we have seen n into n minus 1 additions and n square multiplications. If I solve the same problem by using Radix-2 FFT, whether it may be whatever it may be, the number of complex additions involved in that particular is n into log n base 2. Okay, there it is n into n minus 1. Here number of complex additions is n into log n base 2, that is complex additions. Similarly, how many number of complex multiplication that happens in this particular FFT means that is n by 2 into log n base 2. Okay, you can see the differences. What the computation in the DFT, that is number of additions and number of multiplications, and what is the computation in the Radix-2 FFT, that is number of complex additions and complex multiplications. Fine. Okay, after doing this particular computation both in DFT and FFT, so how much percentage of saving we are doing means, for that we have a simple formula. So in addition, how much percentage I am saving means, that is 100 minus number of additions in FFTs, that is the number of additions in FFT done by number of additions done in the DFT into 100. So by doing this particular thing for a particular problem, we can see how much percentage we can seen in both DFT and FFT. Similarly, how much saving in multiplication means 100 minus number of multiplications in the FFT, that means this formula, number of multiplications in the FFT divided by number of multiplications in the DFT into 100. So by solving this particular, we can see how much percentage saving in additions and how much percentage savings in the multiplications. For that, I have taken one example. If n is equal to 1024, if n is equal to the number of sequences is 1024, you can see here direct computation in DFT. How many additions in this we are doing means, see here, n into n minus 1, that is 1024 into 1024 minus 1. So that means 104755 number of additions is happening in the DFT. Similarly, how many number of multiplications we are doing means n squared, that is 1024 whole square, that is 1048576 number of multiplications is happened in this direct computation in the DFT. Same number if we take in the Radix-2 FFT, now you can see number of complex additions, that is n into log n base 2. If I solve that, I can see only 10 to 40 number of additions. You can compare these two things. You please compare these two things. How many number of additions happen both for the both number, that is n is equal to 1024. You can see both in DFT and FFT. You can see the difference. How much difference you can see here. Similarly, if I see the complex additions, complex multiplication in the FFT, you can see that is 5120, and you can see here DFT 1048576. With this particular tabular column, you can conclude, you will get a clarity, that means how much number of complex additions and complex multiplication is happening in both the DFT and FFT. So we will see how much saving is happened. For the same number, see number of additions FFT divided by number of addition in DFT. We have seen in the previous tabular column, number of additions in the FFT is 1024 and the number of additions in the DFT is 104755. So by solving this, 99% of saving in addition is happened. Similarly, how much number of saving in the multiplication? Number of multiplication we have seen in the previous table, 5120 for FFT and 10,48576 for the multiplications in the DFT. So by solving this, 99.5% of saving happens in the FFT. If I use FFT over DFT, 99% saving in the addition and 99.5% saving in the multiplications happens. A small comparison table, just what we have discussed in the previous slides, complex multiplication and complex addition. So for complex multiplication in DFT, it is n square, whereas for FFT, it is n by 2 log n base 2. And similarly, for the complex addition, it is n into n minus 1, whereas in FFT, it is n into log base n base 2. So with this, we can conclude that what is the computation efficiency of FFT over DFT? Then how much we are going to save both in the FFT when we compare with the DFT. So now everyone will get a clarity that why we are going with the fast Fourier transform when we have the DFT. Fine. Now, but here one important factors involves when we are going to discuss about this particular problems. One important factors will come into case, that is twiddle factor. So see here, due to the efficiency of FFT, it is used for spectrum analysis, convolutions, correlations and linear filtering. So by the advantages of FFT, it will use in all spectrum analysis, convolution part, correlations and linear filtering. Okay, with the advantages of FFT, it uses in all these particular criteria. And similarly, FFT reduces the problem of calculating the endpoint DFT to that of calculating many smaller sized DFT. Okay, end problem, what it does, it reduces the solving of a large number of endpoint DFT, which we have seen in the previous problems. And finally, these three main properties we need to keep it in mind. So the properties of the twiddle factor. Why? Because when we are solving this FFT, one particular parameter will come across, which is nothing but W base n. Okay, so this is said to be a twiddle factor. So for this, we need to keep it in mind. We need to focus on these particular three properties, that is Wn to the power of k plus n by 2 is equal to this one, e power minus j 2 pi k by n into e power minus j pi, that is equal to minus Wn power k. This is said to be a symmetry property, and for the same, Wn to the power of k plus n is equal to Wn power k, which is the periodicity property, and this is the main thing. Wn to the power of m is equal to, we can write it as W to base n by m. So this is the main property, we need to keep it in mind. Okay, with the help of these three properties, we will solve the values which is present in the twiddle factors. We'll see in the upcoming slides how we are going to solve these particular twiddle factor values. Fine. Now we'll see just a small proof related to the symmetry property and periodicity property. For that, I have considered Wn to the power of k plus n is equal to Wn power k, which is a periodicity property. So for this, let Wn is equal to e power minus j 2 pi by n. I am considering W base n is equal to e power minus j 2 pi by n. So I am taking LHS. I am considering the LHS, that is Wn to the power of k plus n. So instead of Wn to the power of, I am writing here W e power minus j 2 pi by n into k plus n. Fine. After writing this, e power a plus n, e power a plus b is equal to e to the power of a, e to the power of b I have written. So this will become 1. Why? Because we can write e power minus j 2 pi is equal to cos 2 pi minus j 2 pi, which the value will be equal to 1. For that, e power minus j 2 pi is equal to 1. Now, Wn to the power of k plus n is equal to e power minus j 2 pi by n into k. So I am writing this by keeping that k factor outside. Now you can see what is this value, we have already known Wn. So for that, instead of this particular, I have written Wn, so that Wn to the power of k plus n is equal to Wn power k, which is a periodicity property. Fine, as a simple property which it will be helpful in the solving problems. Similarly, coming to the symmetry property, same, I am considering the LHS, so Wn to the power of k plus n by 2. Same, let Wn is equal to e power minus j 2 pi by n. So instead of this Wn, I am writing e power minus j 2 pi by n. So I have splitted this, and same, this value will be equal to, so same, this value will be equal to 1. Why? Because of this particular formula. So instead of that, e power minus j pi na, so that's why minus 1. So minus 1. So e power minus j 2 pi by n in power k, where this value we know that Wn. Here already we got this minus value. Why? Because e power minus j pi. That's why this value will be equal to minus 1. So Wn to the power of k plus n by 2 can be written as minus Wn to the power of k, which we are calling it as a symmetry property. So with these three properties, it will be very helpful to solve the fast Fourier transformation problems. Fine. Now, I told you that how this fast Fourier transform is become more advantageous and more important when we consider to the DFT means because of these particular two methods. So there are two methods in divide and conquer approach. We have seen in the classification slide. So here decimation in time FFT algorithm and decimation in frequency FFT algorithm. So decimation in time and decimation in frequency, because of these particular two approaches, FFT has become more important than that of the DFT. In this session, we will discuss about the decimation in time. Later we will see what is decimation in frequency. Both are equal, small differences. If we get a clarity in this decimation time, automatically you can solve this decimation in frequency and inverse decimation in frequency, IDFT. Okay. Now, in this session, we will see what is decimation in time. Fine. It is very important. What is decimation in time? and decimation in frequency. So here, this is the main thing you need to find. Divide and conquer. The sequence which is given will be divided, and then that division will be executed. So each part will be executed. After division, each part will be executed. This is possible if the length of the sequence is chosen. You have to keep it in mind the formula n is equal to r to the power of m. So what is r? R is nothing but the radix. What is r? R is nothing but radix. So r is called the radix of the FFT. So we can, it will be helpful to keep it in mind. Why? Because it will be a MCQ questions for your competitive exams. So capital N is equal to r power m. So what is r? R is said to be a radix of the FFT. That r may be the most practically implemented choice. Mostly choose value for the r will be r is equal to 2. Why? Because I can take a small example. If n is equal to 8, okay, if n is equal to 8, first what I am going to do, n is equal to 8, then n is equal to, I am dividing, I need to divide. That is, next I want to divide means n is equal to 8 means 8 by 2, which is equal to 4, then 4 by 2, which is equal to 2. Finally, I need to get this value 2. Okay, so that's why choose the value r is equal to 2. That means I am dividing the 8 length. The length 8 is divided into 3 stages. Stage 1, n is equal to 8. Stage 2, 8 by 2, that is equal to 4. And stage 3, 4 by 2, which is equal to 2. So this final value which is remained here is said to be a radix, and r is equal to 2. So that's why the most practically implemented choice for r is equal to 2 leads to Radix-2 FFT. That's why we are calling this as Radix-2 FFT algorithm. Okay, so see what I have told here. With n is equal to 2 power 1, what is r? What is r is equal to 2? R is equal to 2 now, so 2 power m. So the efficient computation is achieved by breaking the n point, n is equal to 8. I am breaking DFT into 2n by 2, that is n by 2 plus n by 2. So 2n by 2. I will show you that in the upcoming slide with the help of a block diagram. So the n value will be divided into n by 2, and these 2n by 2 will be subdivided into n by 4, n by 4, n by 4 and n by 4. So totally, finally, how much we are going to get? 2 value. So here we are going to get 4 value and n is equal to 8. Like this, first the n point is divided into n by 2, and then the next breaking n by 2 divided into next n by 4 points. Like this, we are going to divide the value of n is equal to 8. Then after division, these particular divided will be computed. So these approaches will be concurrent, which is nothing but for each subdivision we will do the computation. So here you can get the example. Here n is equal to 8. So that is x of 0 to 7, which is n is equal to 8. So this n is equal to 8 has been subdivided into 2, that is 2-point DFT and 2-point DFT. That is n is n by 2 and n by 2. That is 8 by 2, which is equal to 4. 8 by 2, which is equal to 4. You can see here 1, 2, 3, 4, 1, 2, 3, 4. Fine. So after dividing, we will have some computation on these particular values, and then this n by 2 will be subdivided into n by 4, n by 4, n by 4 and n by 4. N by 4 means which is 2 point. So see here 1, 2, 1, 2, 1, 2, 1, 2 like this. That is combined 4-point DFT, which we are calling it as a 8-point DFT, which is subdivided into 4-point DFT, which subdivided into 2-point DFT. Like this decimation in time algorithm will be decomposed from 8 to 2 values. Okay, so this is the simple block diagram of the decimation in time for the value n is equal to 8. Clear? Fine. Before solving the problem, just we will see what is a simple mathematical expression of this DIT FFT. For this, what I am going to do means, as we have discussed, this time domain sequence will be subdivided into 2. That is, if n is equal to 8, it will be divided into 4, and 4 will be divided into 2. Like so, for that, I am considering the time domain sequence x of n is decimated into n by 2 point. No, so I am considering n value. So for this n value, I am subdividing into n by 2, n by 2. So that is half part. Okay, na? Fine. So one composed of even index. So first half I am considering it as even index, and second part I am considering it as odd index. So the end point is subdivided into 2, that is n by 2, n by 2. So in this subdivision, first n by 2 I am considering as even, and second subdivision I am considering as odd indexed value. So for that, g of n is equal to x of 2n. So if we multiply every value with the 2, it will becomes even. So for even sub-indexed value, I am considering it with g of n. G of n is equal to x of 2n. Similarly, for the odd value, I am considering it with h of n, that is x of 2n plus 1. Okay, 2 into 1, which is 2, plus 1, which is 3. So that means all odd indexed value will form with the second equation. I think you got a clarity. That is, have divided that n into 2 subdivisions. One is even and another one is odd. Fine. Now here I am considering the endpoint DFT. Already we have seen in the second slide the equation of DFT, x of k is equal to summation n is equal to 0 to n minus 1 x of n, and here comes the factor which is a twiddle factor. This, instead of e power minus j2 pi, I am writing here wn to the power of nk. Okay, so that's why I told you, please keep it in mind, the three properties. Instead of e power minus j2 pi, I'm replacing that with a factor which is known as twiddle factor, that is w n power small n into k. So now what I'm writing, I'm subdividing this equation into 2. Already here I shown you first half part which is even one, and second half part which is a odd one. That is, summation n is equal to 0 to n minus 1 for even x of n wn to the power of nk. For summation n is equal to 0 to n minus 1 which is odd, x of n wn to the power of nk. So here instead of x of n, I am replacing that with x of 2n. Instead of x of n, that is, I am replacing it with x of 2n plus 1. We will see that. See here. So this is even. So this is even. That's why instead of x of n, I am writing it with x of 2n, and this is odd. So instead of x of n, I am writing that with x of 2n plus 1. That means in the n place, I am substituting it with 2n plus 1. Here also 2n. So instead of n, I am substituting it with 2n. Whatever the places n, substituting in the even, it is with 2n, and in odd, it is with 2n plus 1. So here I have wn to the power of 2nk into wn to the power of k. Here I have splitted that. After splitting, I took out that particular factor outside summation part. Now you can see even part and the odd part. Here wn to the power of 2nk, wn to the power of 2nk, and summation is same. So finalize the equation using the third property. What is third property? wn to the power of 2nk is equal to w power of nk n by 2. These two will become, which is the third property. The same thing here it has been written, w to the power of nk base n by 2, and here also w to the power of nk base n by 2. Now you can see what we can take common here. Summation n is equal to 0 to n by 2 minus 1, w to the power of nk base n by 2. If we take common, we will write this. First equation, what is 2n? 2n is nothing but gn is equal to 2n, and here also x of 2n plus 1 is equal to h of n. From the equation 1 and 2. From the equation 1 and 2, I am replacing x of 2n with gn and x of 2n plus with h of n. Now, this can be after DFT, what I can write directly, x of k is equal to, so these total will be in the form of g of k, and this total is in the form of h of k. Okay, so that's the main equation we obtained here. That is, DFT of x of k is equal to g of k plus the twiddle factor. You should keep it in mind, don't forget, wn to the power of k into h of k. Okay, now this is for the DFT. Fine. Now where g of k and h of k are the n by 2 point, how much? N by 2. We have divided that into n by 2. N value has been divided into n by 2. For that, the g of k and h of k are the periodicity of n by 2. So I can write g of k plus n by 2 is equal to G of k, and h of k plus n by 2 is equal to h of k. Like that also we can write. Why? Because we have take the periodicity of n by 2. So with this, the final equation, what I can write by using the symmetry property, x of k is equal to g of k minus n by 2 plus w n to the power of k into h of k minus n by 2 for the condition n by 2 less than or equal to k less than or equal to n minus 1. So for this equation, for this third and sixth equation, that is for the third equation and the sixth equation, this is the butterfly diagram. See here. So xk is equal to, so what is xk? You can see here, xk is equal to first gk. So gk is coming here. I will write here. Xk is equal to gk plus from the down. What the value is coming from down? hk, like this. That is plus, and we should keep it in mind. There is one factor which is wn power k into hk. You can see the equation, which is third equation. Xk is equal to g of k plus wn to the power of k into h of k plus wn to the power of k into h of k. Fine, it is the value for x of k. Similarly, you can take this for x of k plus n by 2 where the sixth equation will be formed. That is g of k minus, you can see here, x of k plus n by 2. For this value, what I am going to get means, I am getting the value gk, and here the twiddle factor is minus wn to the power of k into h of k. A small difference for the n by 2 periodicity, the difference is minus. Here it will be plus and here it will be minus. So you should keep it in mind. In the butterfly diagram, whatever the direction it is going up, it will be in a plus, and whatever the direction it is coming down, it will be minus because of this periodicity property. Fine. So this is the simple butterfly diagram where in each and every stage we will see this kind of butterfly notations. So with this particular third and fourth equation, third and sixth equation, so you know that third equation is this one and sixth equation is what we got this. So for example, I am taking for n is equal to 8. For n is equal to 8, what will be the value of x of k values? So for this, in the third equation, I am substituting k is equal to 0 to 3. So I am substituting the value k is equal to 0 to 3 in third equation and k is equal to 4 to 7 in sixth equation. So by doing that, what I am going to get, first value x of 0 is equal to g of 0 plus wn to the power of 0 h. Actually here n, so instead of n we are going to keep 8. Why? Because we have taken the example n is equal to 8. Fine. Similarly, if I place k is equal to 1, g of n, w to the power of 1, h of 1. Similarly, for x of x is equal to 2, x is equal to 3. 4 equations we got for the third equation. And similarly, if I substitute k is equal to 4 to 7, for first x of 4 is equal to, see here, 4 minus, what is n by 2? What is the value of n here? 8. 8 by 2 means 4. That is 4 minus 4, 0. That is g of 0 minus, here it is, the value is minus. Why? Because we are taking the n by 2. The value is minus wn to the power of 4. What is value? First, for the value we are taking here, for n is equal to 4 we are doing. So here instead of k, it is 4 and h of 4 minus 8 by 2, which will be equal to 0. Similarly, if I substitute k is equal to 5, k is equal to 6 and k is equal to 7. So these are the total 8 equations we will get with the help of third and fourth equation, third and sixth equation. So with the help of this third and sixth equation, if we see the bit reversal, this is the main thing we have to keep it in mind. The equation will be in the form of sequence x of 0, 1, 2, 3, 4, 5, 6. For n is equal to 8, they will give the equations 0, 1, 2, 3, 4, 5, 6, 7 equation. So the indexed value is, we know that 0, 1, 2, 3, 4, 5, 6, 7. For this, I am writing that in the binary representation. For 0, it is 000. For 1, it is 001. Like that, for all 80 values, I have written that in the binary form of index. If I bit reverse this form of index, so if I bit reverse, for example, here 001, I am reverse this. Totally, I reverse this. 100. 010 means if I reverse also, it will be same. and 011 means 110. 100 means 001. If I bit reverse, this is the values I got. And if you take the index values, this for this bit reverse form, all zeros means 0, 100 means it is 4. See here, 100 means 4, 010 means 2, same value, 110 means 6 value. Like this, decimal representation I have indicated. Now here, final input sequence order what I am going to get means 04261537. That means if the sequence is given in a order of 0 to 7, what is the final input sequence I need to keep in means first even part, that is 04261537. I will show that in the problem how this particular tabular column will be helpful while solving the problem. Just keep it in mind, we need to do the bit reverse for the input sequence, and for doing that, this is the process. The given input sequence, take the index value, take the binary form of that index value, just bit reverse that particular binary form of index value so that the decimal representation will be formed, which is the final input sequence order. This is the order we need to keep in the input sequence. See, this is the flow graph of 8-point decimation in time FFT algorithm using the butterfly. First, they will give this order 0, 1, 2, 3, 4, 5, 6, 7. After giving that, after solving all the things, this input sequence you can see here 0, 4, 2, 6. First part will be even and 1, 5, 3, 7 which is odd. Just previously we have seen how the input sequence, this is the input sequence. How the input sequence is going to happen means with the help of the tabular column, that conversion, that input sequence will be formed like this 0, 4, 2, 6 and 1, 5, 3, 7. That means if the total sequence n is equal to 8 given, with the help of this butterfly diagram, that will be divided into 4 parts, block representation. So after solving this, we will get the values here. Okay. Then with the help of this, that means after completion of this particular criteria, this is first stage. This is first stage, this is second stage, and this is the third stage. If n is equal to 8, how many stages we will get means 2 power 3. So 3 stages will be formed, first, second and third. So in the first stage, after solving, that n is equal to 8 will be divided into n is equal to 4 and n equal to 4. After getting this particular new input sequences, then this n by 4 will be subdivided into n by 2, that is 4 by 2, 4 by 2. So here 2 values, that is 1, 2, 3, 4. So 2 sequences from the divide, and this is the final input sequence what we are going to get. That means while asking the problem, they will give the sequences from x of 0 to x of 7. After drawing this x of 0 to x of 7, by solving all these particular stages, and finally the x of n, which is the DFT, DIT, DFT. First they will give the DIT presentation, that is x of k. After solving that, we are going to get the values of all x of n. That is decimation in time. We are reducing all the decimation in time. We are reducing all the time sequences with the help of decimation in time in the FFT algorithm. So this is the main butterfly diagram of the DIT FFT algorithm for n is equal to 8. And you can see here the twiddle factors. Why I told you that, please we need to keep it in mind, that twiddle factor will form here. For every stages, this is the twiddle factor, W8 to the power of 0, 8 to the power of 1, 8 2 and 8 3. After it is subdivided, W8 to the power of 0, W8 to the power of 2, W8 to the power of 0, W8 to the power of 2. After it is subdivided, only 8 power 0, 8 power 0, 8 power 0, 8 power 0. Whatever the problem we are solving, this is the main block diagram, this is the main decimation in time algorithm diagram you will get. Okay. So with the help of this diagram, whatever the sequences they are given, please take all the sequences here and start doing the problem. Okay. So this is the finalized flow graph of the 8-point decimation in time FFT algorithm using the butterfly. And simple, a flow graph of 4-point decimation. Here previously we have seen n is equal to 8, now n is equal to 4. If they give for n is equal to 4, just this is the simple, n is equal to 4 they have given. After that we are divided into n by 2, that is 4 by 2, 4 by 2. That is 2 sequences. and you can see the sequence 0, 1, 2, 3, 4 sequences. And what we are going to get the input sequence? Bit reversal. Bit reversal means x of 0, x of 2, 1, 3. After doing the bit reversal, this is the input sequence we are going to get. First even part, second odd part. Fine. So whatever the sequence they are giving, we need to bit reverse, and finally after getting the values here, carefully we have to give the value to the respective sequences. X of 0, x of 2, x of 1 and x of 3. For example, if I get the value here 2, 1, 3, 4, the same thing you have to give. For x of 0 is equal to 2, x of 2 is equal to 1, x of 1 is equal to 3, x of 3 is equal to 4. By in fast, what some of the students will do means they will give the values as x of 0 is equal to 2, x of 1 is equal to 1, x of 2 is equal to 3 and x of 3 is equal to 4. In a hurry mode, what they are going to do, they will give the direct sequences, that is x of 0 is equal to 2, x of 2 instead of 2 they will write x of 1, instead of 1 they will write x of 2. So the input sequence will become wrong. That's why be careful while you are doing after getting the value will get correctly, but after representing, that is y of n is equal to, after representing that input sequence, you need to make careful that give the sequences to the respective values. Fine. X of 0, x of 2, x of 1 and x of 3. Clear? So with this you get a clarity that how we need to draw the butterfly diagram for n is equal to 8 and n is equal to 4. So simple block diagram, as I told you, the natural order DFT sequence will be given like this. This is the third stage. First what we are going to do, first stage, second stage and third stage. This is for n is equal to 8. I told you that n is equal to 8 means 2 power 3. So how many stages we are going to get? We are going to get the 3 stages. And this is the finalized base block diagram of the butterfly DIT FFT algorithm. See, all the DFT are being divided and conquered. The approach is like this. 3 stages in the computation of n is equal to 8. And how the twiddle factor values, in the previous slide I told you that what is the equation we will get here. For the first, if the butterfly is going to the upper side, the value will be equal to plus, and if we are taking the value to the downside, the value will be minus. See, the notation, the equation will be same, but the notation will be different. While we are doing the computation for the upper arrow, it should be plus, and if we are doing the value for the downside arrow, it should be minus. Why? Because here the twiddle factor will be minus wn to the power of k. It will be equal to minus 1. You should be careful while doing this problem. While the value is going, if you are computing the value for the upper side, the value, take the notation plus. And if you are doing the computation for the downside flow, you should take the computation, you should take the notation as minus. Just be careful with this twiddle factor, with this particular block diagram while solving the values for the upper flow and down flow of the butterfly diagram. And this is a small differences you can see for number of points for n is equal to 4, n is equal to 8, 16, 32, 64, 256, 1024. What will be the direct computation? That means in the DFT, what is the direct computation means? We have already seen the equation for number of complex multiplication, it is n square, and complex addition, it is n square minus n. So if we do this, this is the value. If we do that in the direct computation, these are the value we are going to get. And same thing if you compare with the DIT FFT, see the differences. That means how many times the improvement you can see here, 4 times improvement. If n is equal to 4, how much time it is improvement for the multiplication? 4 times improvement in the multiplication. Like this, for different types of for different values of n, you can see how much improvements in the speed when we compare it with the DFT and DIT FFT. Related related formulas for the operation for complex addition and multiplication, which we have seen already in the previous slide, and small comparison for all different values of the n. And here you need to keep it in mind, while you have seen in the previous diagram, we get the values of different w8 to the power of 0, w8 to the power of 1, w8 to the power of 2, 8 to the power of 3, total 4 values. Similarly, 8 power 0, W8 power 2, and finally W8 to the power of 0. So that means we got some twiddle factors. For this, how we are going to get the values, solve the values mean, we know already what is Wn. Wn is nothing but e power minus j 2 pi by n. Fine. Now for n is equal to 8, if we do the values W8 means instead of 8 n, I am writing it with capital 8. So what I am going to get here, e to the power of minus j pi by 4. That means for the n is equal to 8, what is the equation I am going to get? E power minus j pi by 4. Now for k is equal to 0, what is the value? W8 to the power of 0 is equal to e power 0. That means total value is 0 na? That's why e power 0 is equal to 1. Now for k is equal to 1, for one value, e power minus j 2 pi by 4 into 1. 1 means I can write this e power minus j pi by 4 as cos pi by 4 minus j sin by pi by 4. The value what I am going to get is this one. Similarly, for k is equal to 2, that is I am multiplying that with 2. So I get 2 ones are 2 2. What I am going to get here, e power minus j pi by 2, where I can write it as cos pi by 2 minus j sin pi by 2, and the value is minus j. Similarly, when we multiply that with k is equal to 3, that is 3, what I am going to get, minus j 3 pi by 4, which is cos 3 pi by 4 minus j sin 3 pi by 4. That means whatever the value, whatever the problem you take, the values will be equal. That is, if you want to take the value W8 to the power of 0, it will be equal to 1. In every problem, in each and every different problems, the sequence will be changed, but the twiddle factor values will not change. Why? Because it is a fixed value. We have seen already what the values we are going to get for different 1, 2, 3. So W8 to the power of 0 means you definitely compulsory you take it, the value will be equal to 1. And if it is W8 to the power of 1, just substitute instead of that 0.707 minus j 0.707. If it is W8 to the power of 0, 2, just write it with the value minus j. Like this, whatever the problem you are solving, just substitute the values instead of W8 to the power of 0, this. Fine. And how we are going to draw these particular diagrams? If you see here, I got the total sequences. First, after drawing this sequence, why the name we are calling it as a butterfly? See here, these circles represents butterfly representation. You can see the circular, the combination of blue and red lines will form 4 points where it represents in the form of butterfly representation. So that circles are where the FFT butterflies. And finally, this is the finalized diagram. If the problem is given, how we are going to get the value. So the sequences is given, and how the sequences, input sequence, what we are going to get this equation. That means how this is going to represent a small diagram I have taken to which it will be easy. So just one example I have taken simply for n is equal to 4. So the sequence here n is equal to 4. That is x of n is equal to 1, 2, 3, 4 given, and he has to find out the values FFT for the sequence using DIT FFT. Now see here, what is the value given here? 1, 2, 3, 4. So here the value sequence given here is x of n is equal to, just I will write here, x of n is equal to x of 0, x of 1, x of 2 and x of 3. First you need to write like this. Why? Because 1, 2, 3, 4. Why? Because while you are inserting that particular values here, you need to insert properly. For x of 0 the value is equal to 1, for x of 2 the value is equal to 3, for x of n the value is equal to 2, and for x of 3 the value is equal to 4. I told you, in a hurry mode what you will write? You will write 1, 2, 3, 4. It is wrong. Okay. While inserting the values in the input sequence, just follow this order so that the input sequence values will not be interchangeable. Fine. Now for n is equal to 4, W4 to the power of 0 and W4 to the power of 0 and W4 to the power of 0 and W4 to the power of 1. For n is equal to 4 diagram, it is a simple diagram, simple butterfly diagram. Now what is the value I am going to get here means, just one value I will do here, that is x of 0, and the flow is upside, okay na, plus W4 to the power of 0 into what is here, x of 2. I think you got first notation x of 0. For value x of 0 I have given, and from here the value x of 2 into w 4 to the power of 0. That is, what is the value here? X of 0 is equal to 1 plus w 4 to the power of 0 is equal to w 4 to the power of 0 is equal to 1. The value of this w 4 to the power of 0 is equal to 1, and x of 2 is equal to 3. That is 1 plus 3, which is equal to 4. I think the value what we got here is x of 4. Similarly, I told you here the same equation, but the notations will be different. X of 0 minus, why? Because flow to the downside, the twiddle factor value is minus w 4 to the power of 0 into x of 2. So if you see here, so x of 0 is equal to 1 minus 1 into what is here value 3. So 1 minus 3, that is equal to minus 2. So you got the value here minus 2. Like that, for each and every stage you need to find out the values. So that I got 4 minus 2, 6 minus 2. Now the first stage is completed. Now we got the new input sequences. Don't consider these sequences now. We completed the first sequence with the first stage, and I got the values 4 minus 2, 6 minus 2. Now these are the new input sequences. Here I am doing the second stage. In the second stage, after doing the same computation, finally what the value I am going to get here is x of 0 is equal to, if I do all the values, 10 minus 2 plus 2j minus 2 minus 2 minus 2j. So that means for 2 power, for n is equal to 4, 2 power 2. That means how many stages? 2 stages. First stage, second stage. In the first stage I have done, and don't consider that first input sequences. Whatever the new sequences you got, you please consider this sequence and start doing the second stage. After doing that, final equations, final values what we got here is nothing but the x of k values. Like this, for n is equal to 4, whatever the value sequences they have given, the value for w4 to the power of 0 is equal to 1. Why? Because you can see here w4 to the power of 0 is equal to plus 1 if it is for all the values 1, 0, 1, 2, 3 values. So for w4 to the power of 0 is equal to 1, w4 to the power of 1 is equal to minus j, w4 to the power of 2 is equal to minus 1, and w4 to the power of 3 is equal to plus j. So these are the fixed value for the butterfly diagram if n is equal to 4. So same thing here also we will write w4 to the power of 0 is equal to 1 and w4 to the power of 1 is equal to minus j. So like this, the values will be computed and we are going to get the final value of x of k. So this is the simple formula, problem for n is equal to 4. So what I want to tell you is that for the value, for the sequences what they have given, it will be different, but the butterfly diagram will be same. The diagram will be in the same representation, but the sequence will be changed. The twiddle factor will be same, the values will be same, everything will be same. What the difference here means, only the sequences will be differences. The sequences will be changed, but the process will be same for all the values for n is equal to 4. Like this. Similarly, 8 for n is equal to 8. Here you need to take time and do the problem clearly and neatly. Why? Because if you miss one value, total entire problem will become 0. So same here. They have given the value x of n. So x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. Same. First subdivision, I am dividing that into two half parts. First even part, second even part. So first 0, 4, 2, 6. First even part 1, 5, 3, 7. Same values I have written here. First input sequence, we can see the twiddle factor w8 to the power of 0, w8 to the power of 0, everything. So for here, first just I will write x of 0 plus w8 to the power of 0 into x of 2. X of 2 na? Sorry, x of 1. Sorry, x of 2. It is x of 2 only. Even sequence na? Fine. So x of 0 is equal to 0 plus, what is w8 to the power of 0? 1. 1 into x of 2 is 4. So what I am going to get? 0 plus 4 is equal to 4. So the new value what I got here is 4. Like that, every value. So for this also I will draw x of 0 minus, why? Because float, the total factor value is minus w8 to the power of 0 x of 2. So for this, same 0 minus of 1 into 4. So what I am going to get? Minus 4. So here the value I am going to get is minus 4. Like this, we need to do all the values for the 4. The values what I got here is see 4 minus 4 I got here. 4 minus 4. So same computation, the first stage is completed. The first stage is completed and I got the new input sequences. These are the new input sequences. 4 minus 4, 8 minus 4, 6 minus 4, 10 minus 4. Now we need to do the same. Second stage after doing this, here the two digit factor will be formed. W8 to the power of 0, W8 to the power of 2. After doing this, what I am going to get? I am going to get the new input sequences here. You can see I got new input sequences. Now we need to clear the third stage. We want to do now the third stage. Same computation will be done, and finally what I am going to get is the final values of x of k. So these are capital X of 1, X of 2, X of 3. All the values will be formed. Here the twiddle factors, you need to carefully take the values here and carefully multiply the twiddle factor with the values of x of 0 and x input sequences. Then only you will get the corrective values. So like this, the total values what I am going to get will be in the form of decimation in time. So this is all about the decimation frequency. In the next lecture, we will see the another approach, which is decimation in frequency. Now we have seen the decimation in time fast Fourier. In the next lecture, we will see what is the process of decimation in frequency, followed by inverse DFT also we will see, and we'll see take one problem and solve the same thing. So thank you very much.